Thank you very much. Let me start by thanking the organizer for putting up this very nice conference and also for inviting me. So I've known Gordon for a very long time, really. I mean, we were both in high school when we met. And we were going together to some of these math competitions. And then he was some sort of an older brother to me. So he's not so much older, but mathematically he was always way ahead. So he gave me a lot of very useful advice from the beginning. He told me like what to read, what to ignore, what classes to take, what not to take. And he also told me that representation theory is like the best thing in Zagreb. And especially he singled out Marko as the guy to be around. And then when I was a graduate student at University of Utah, he just moved there about the same time when I was there. And then so with my advisor, I was doing some very abstract things like the derived categories and so on. But with Gordon, I was talking a lot, and we did even some work together about some much more down-to-earth representation theory, very concrete. So that was very valuable to me to learn that side also. I think with just the abstract stuff, it would be very hard to start doing something else. So I'm grateful to Gordon for our decades-long friendship. So happy birthday.
I would also like to thank everybody coming, in particular organizers, and especially Vitek, I mean, who's, I'm sure, possibly major force behind. I mean, certainly, my, most prolific collaborator. And I would like to correct Dipendra, who thought that Dipendra said that he knows me probably the longest after Marko Tadic, obviously. Pavle takes number one.
You cannot beat high schools. Okay, so let's start with the talk. So this is some funding information. I have to put it here for the grand purposes, but also I like to put it because there are some nice colors, you see. So I'm not so good with putting pictures into slides. So some color is welcome. So what I'm going to talk about is joint work with S.Mehdi, with D.Vogan and R.Zierau, and it was recently published in Advances. So let's first set up some notation and the setting. So GR is a real reductive Lie group, often assumed connected. Later on, it will be simple and linear. And then theta will denote a fixed Cartan involution of this real group GR. And we assume that KR, that's the fixed points of theta in GR, we assume that's a maximal compact subgroup. So for example, you can think of this semi-simple connected with finite center. That would be one possible setting. And so then Gothic G will be the complexified Lie algebra of GR, and then G and K will be reserved for the complex Lie groups. So we assume the GR and KR can be complexified to G and K, like you can do for classical groups. Like if your GR is, for example, SUPQ, then this G would be SLP plus Q comma C. Okay, and then we'll study admissible representations of GR through their Harish-Chandra modules. So they can be defined abstractly. They are finite length G modules with a compatible locally finite action of K. So I suppose everybody's familiar with that, so I don't have to talk much about it. Okay, then we'll fix a non-degenerate invariant symmetric bilinear form B on G. So in semi-simple examples, it would be the killing form, would be the obvious choice. For some of the reductive groups, you have to extend the killing form over the center. You can also take the trace form for the matrix groups. And then corresponding to that Cartan involution, there is a Cartan decomposition, K plus P. So K is the Lie algebra of K, and P is the -1 eigenspace for theta. Sometimes denoted S. In some talks, that was denoted by S. So then C of P will be the Clifford algebra of P with respect to B. So B is still non-degenerate on P. And we consider the Clifford algebra. We already saw this in some talks. So it's the associative algebra with unit generated by P. And the relations are the anti-commutators should be xy plus yx should be -2bxy. And then we take any basis bi of P and take di to be the dual basis with respect to B. And then the Dirac operator as defined by Parthasarathi is sum of bi tensor di inside U of G tensor Clifford of P. So this bi is in U of G and di is in Clifford algebra of P. So it's an analog of Dirac's Dirac operator, of course, which is much older. But this turned out to be useful. So Parthasarathi used it to construct the discrete series representations. So one of the first properties, so it's defined using a basis, but it's in fact independent of this basis. And by the same reason, it is also K invariant for the adjoint actions on both factors. And then there is a nice formula for D squared. It's something called the spin Laplacian. So it's something like the difference of Casimirs of G and K. But for K, you don't take K just in the first factor, but you take some sort of diagonal version because K can also be mapped into the Clifford algebra, and then you take the diagonal copy of K. And then this produces some lower order spin terms, let's say. That's why it's called the spin Laplacian. I'm not gonna write the precise formula, but approximately it's what I told you. So to define the Dirac index, let's first define Dirac cohomology. So let M be a Harish-Chandra module, and let's assume it has infinitesimal character. So we assume all the time it's finite length. So it's a direct sum of modules with generalized infinitesimal character. But let's for now assume it has actually infinitesimal character. And then let S be a spin module for the Clifford algebra. So you can construct it as the exterior algebra of a maximal isotropic subspace P plus of P. And then the action is, so P plus would act by wedging, going up, and P minus, that's some dual isotropic subspace, would act by contractions. And that's more or less all of the generators for C of P. If you have one more, then you have to act it somewhere. So if the dimension of P is odd, then you have an extra element and you have to define the action separately. And then you have two choices. In the even case, there is only this one irreducible module for the Clifford algebra up to isomorphism. And now the point is, so now this extended M tensored with the spin module, this will have an action of D. And then we can consider the cohomology. The cohomology should be something like kernel module of the image. Well, here the image is not really contained in the kernel, but you can still mod out the intersection of image and kernel. So that's called, this is some generalized sort of cohomology. And so it is because of this K invariance of D, it becomes a module not exactly for K, but for some double cover, which is called the spin double cover. The point is that K does not act on S, but the spin double cover acts on S through this spin group, which is contained in the Clifford algebra. And now we are assuming M is of finite length. So this Dirac cohomology will be finite dimensional module over K tilde. And then the main general result about this Dirac cohomology, if it's non-zero, which is very often, so generically it is zero, in fact, but for very many interesting examples, it is non-zero. And in those cases, this Dirac cohomology encodes the infinitesimal character. So the infinitesimal character of M can be read off from the Dirac cohomology. This was conjectured by Vogan, proved by Huang and myself. And this kind of started a lot of investigation in several directions. So what's really, how can you read it off? So if you take a K-type inside this Dirac cohomology, look at it infinitesimal character, and that's the G infinitesimal character of M, up to some obvious identifications, and up to Weil group, of course. And then to move to the index, so index is in fact the Euler characteristic of Dirac cohomology. And so it's a little bit cruder because you take some alternating sum, there can be some cancellations. So it's cruder, but it's also easier to work with. It goes through spectral sequences, for example, and so on. So if you want to study the characters, then the character is reflected through the index, through this Euler characteristic. So how do we define this Dirac index? We assume that rank of G is equal to the rank of K. If it's not equal rank, then this definition I'm gonna give would not give you anything non-trivial. But there is a way to modify, to construct something called twisted Dirac index, but I'm not gonna talk about that today. So we'll just assume all the time that G is equal rank. And then in particular dimension of P is even, so there is only one spin module and it is also graded. You can consider the even part and the odd part. So that's even wedges of P plus and odd wedges of P plus. And then D is odd in the Clifford factor, so it's gonna interchange S plus and S minus. So then the Dirac cohomology will decompose into plus part and minus part. And then you take the formal difference. So the Dirac index is the virtual K tilde module, which is defined as the difference, formal difference of the plus part, of the even part and the odd part. Why it's called the index? Because it is the index of some, you can view this D as taking M tensor S plus to M tensor S minus. And then this HDM minus is in fact co-kernel. You can identify it with co-kernel of this D plus. And so this really becomes the index. So this is the kernel, this is the co-kernel of this restricted Dirac operator. So that's why it's called the index. So M has finite length, Dirac cohomology is finite dimensional, then this Dirac index is also finite dimensional as a virtual K tilde module. We can consider its dimension, or virtual dimension. So it's an integer, and it's given by the wild dimension formula for K. So if you have like an integer combination of K types, then you look at dimension of all these K types and take the same, integer linear combination of these dimensions. So you get a number which could be positive or negative or zero. Okay, so now we come to associated variety and cycle. This was already introduced in one of the talks. So I'm going to go over it quickly. So another important geometric invariant of a Harish-Chandra module M, it's associated variety. So to define it, you start with usual filtration of U of G by degree. Then the graded algebra is the symmetric algebra of G, which is the same as the polynomial algebra of G star. And then on any Harish-Chandra module M, you can define good, so-called good filtrations that are compatible with this filtration by degree. And these good, there are several properties, but the main point is that the GRM becomes a finitely generated module over the polynomial algebra. So how would you define one such good filtration? So you take the generators, it's finitely, so M is supposed to be finitely generated. You take the generators, you close them up into some K module, and then take that to be degree 0, and then act by U of G of degree 1, 2, 3, and so on to get the filtered pieces of M. And of course, it's non-unique, but all of these filtrations are equivalent in some sense. In particular, this GRM is well defined. And then the associated variety is the support of this module GRM. So this is a module over the polynomial algebra. So the support is the variety in G star defined by the ideal, which is the annihilator of GRM in the polynomial algebra. So the zero set of the annihilator. And then a good filtration is always K stable. That's one of the conditions. Then in fact, so this K is of degree 1 in this filtration, degree filtration of U of G. So it should increase, but in fact, it's stable, so it doesn't increase. So this means it becomes 0 acting on this GRM. So this means that it's actually a K stable subset of G mod K star or P star. And then in fact, one shows that it's contained in the nilpotent cone, which I denote by NP. So it is a union of closures of some K orbits, denote them by O1 to OL. Then if M is irreducible, then each of these OKs is a real form of a single G orbit in the nilpotent cone NG. So what this means is that there is a G orbit OC inside MG, so that when you act by G on each of these OK, you always get this OC for all K. And this OC bar can be characterized as the associated variety of the annihilator of M. So when the annihilator of M in U of G, that's an ideal, N of M. And then you look at the module U of G divided by that ideal. So that's a U of G module by left action. And then you look at the associated variety, so the support, like before. And then the associated cycle is a formal integer combination of these same orbits that come into the associative variety. And this multiplicity MK is the rank of GRM at a generic point in OK bar. So what is this rank? So you pass to a point, you get a local ring. It has a unique maximal ideal. And then you can divide your module GRM by this ideal I times GRM. And then you get the vector space, and this rank is a dimension of this vector space. So this associated cycle is obviously a finer invariant than the associated variety. If you know this associated cycle, then you know the variety. The associated variety is just the union of this OK bar that are here in the associated cycle, but you also have the multiplicity. So the problem is it's finer, but the multiplicities are usually very hard to compute explicitly. And then if you want to see more about this, there is an old paper by Vaughan, Associated Varieties and Unipotent Representations in some proceedings in '91. Okay, so the next thing we want to mention is the coherent families. So let H be some Cartan subalgebra of G, and let lambda 0 be a regular element of H star, and let capital lambda be the lattice of G integral weights. And then a family of virtual GK modules X lambda, where lambda is in this translate of the weight lattice by lambda 0. This family is called coherent if the first thing for each lambda, X lambda has infinitesimal character lambda. And the second thing is compatibility with tensoring. So if you have a finite dimensional GK module F, then for any lambda, X lambda tensor F is the sum of X lambda plus mu over all mu in delta of F. So delta of F is the multiset of weights. So the weights of F counted with multiplicity. So this is, if you are not very familiar with this notion, then this is a little puzzling because it tells you that tensoring is something very easy and explicit, and you know it's not. But what is the thing? You see, these are just virtual modules, and there could be some cancellations. This lambda plus mu could be Weyl group conjugate to some lambda plus nu, and then you can have some cancellations in this sum, and this is where the complication is restored. So to read about these coherent families, there are various properties. One good place is Vaughan's Green Book. So in particular, there is a proof, and it's really like a long and complicated proof. It takes something like half of the book to be able to do this proof. And that's the following thing. So if you start with the, well, you can say Harish-Chandra module or virtual, doesn't matter. Call it X. If it has a regular infinitesimal character, lambda 0, and then there is a unique coherent family X lambda, which has this X at place lambda 0. So this is called coherent continuation. So with this one module, you immediately get the whole coherent family, and it's uniquely determined. If you start with something of singular infinitesimal character, then you lose uniqueness. There is still a family, but there isn't a unique one, but several of them. And then one way to use this idea of coherent continuation is the following. So if you have some invariant of Harish-Chandra modules, if you can extend this invariant to virtual Harish-Chandra modules, and this typically requires, for example, additivity with respect to short exact sequences that would enable you to extend to virtual Harish-Chandra modules, and then you can study how it varies over the coherent family attached to X. And then in some cases, if it varies nicely, then you get a new invariant. So one such invariant is our Dirac index. It can be defined for virtual Harish-Chandra modules, and it varies coherently over any coherent family in an appropriate sense. And it's based on H star. H is the compact Cartan subalgebra of G. So how do you prove this? So you show that if M has infinitesimal character, then our index that we defined can also be written as M tensor S plus minus M tensor S minus. So this is like Euler-Poincaré principle. This is, you can think of this M tensor with S. S is some exterior algebra, so it's like some complex. And then this would be the alternating sum over the complex. And this is the alternating sum of cohomology. And then you can say, okay, now for these more complicated modules with just generalized infinitesimal character, I can take this as definition. There is something to prove that it's still finite dimensional, for example. And one shows that it has the desired properties. It is also possible to extend our definition of Dirac cohomology to include these modules of finite length, not necessarily with infinitesimal character. And then this index would be, again, the Euler characteristic. But I won't go into that today. And then remember that we studied this index and then we took the dimension. And now one can now think of this as a function. So attach to lambda the dimension of the index of x lambda. And then this extends to a homogeneous polynomial DIP, so Dirac index polynomial of x on H star. And it is given by the wild dimension formula for K, because the index is just a combination of some K modules, and the dimension, you have the wild dimension formula, and it is a polynomial in lambda. So, okay, maybe I should say that it can happen easily, and it happens typically for small representations, that is, I of x lambda is non-zero, but the dimension is 0. This can happen. For example, if you take M to be finite dimensional, then this is the dimension of this is the dimension of M times dimension of S plus minus dimension of S minus, but S plus and S minus, they have the same dimension, so this is always going to be 0. So this dimension is going to be 0 for small representations. For example, for minimal representations, it would be 0, but the index would not be 0. So it's, again, cruder, but then it should be easier to use. Okay, then one property of this Dirac index polynomial, it is W harmonic. W is the Weil group of GH. So this means, well, there are some Laplacians that are 0 on it, but you can also think of it as being a W representation, which does not appear in lower degrees, in polynomials of lower degree. And then this Dirac index polynomial is analogous to Joseph's Goldie rank polynomial. It's defined on the maximally split Cartan subalgebra. And then one piece of this analogy is that, like Goldie rank polynomial, it's also the leading term in the Taylor expansion of the character of some suitable completion of x lambda. But Dirac index polynomial is the leading term on the compact Cartan subgroup, and Goldie rank polynomial is the leading term on the maximally split Cartan subgroup. This is not so difficult to prove. It actually follows from here. You see character of M times character of S plus minus character of S minus is the character of the index, and this is finite dimensional. So that's a sketch of proof. You divide, this is just some wild denominator, this character of S plus minus character of S minus. It's a piece of the wild denominator. Of course, there are still some technical issues. Okay, so a reference for this stuff and many more details and examples is in another paper with S.Mehdi and D.Vogan in 2017 American Journal. And then, so the associated cycle can also be defined for virtual Harish-Chandra modules. This is not immediate because actually it is not additive with respect to short exact sequences. So you have to go around somehow. And we will say more about this a little later. And then here is the fact. So for coherent family X lambda, all X lambda in it have the same associated variety. And the multiplicities, they vary in a polynomial fashion with lambda. So starting from a Harish-Chandra module X, considering the corresponding coherent family X lambda, one obtains the multiplicity polynomials Mk of X. They are again W harmonic. And in general, they are quite different from our Dirac index polynomial. For example, their degrees are usually different. I mean, for Dirac index polynomial, we know the degree. It's the number of the positive roots for K, because it's the wild dimension formula. And then there is a certain interesting class of Harish-Chandra modules where we found a connection. And what we showed then is that our Dirac index polynomial can be obtained as an integer linear combination of the multiplicity polynomials. And more precisely, here is our main result. So now let's assume that the GR is simple, connected, and linear. And still we assume that the G and K have equal rank, because that's when we define the index. And then let's also assume that the Weyl group representation generated by the wild dimension formula for K is Springer. So what this means, there is Springer correspondence. So if you have an orbit, then you can look at its top Borel-Moore homology and you obtain a representation of the Weyl group. This is called Springer correspondence. And you get some of the representations of the Weyl group, not all of them. So those that you obtain are called Springer representations. And so by definition, they would correspond to an orbit. So let's assume that our W representation corresponds to a G orbit OC in the nilpotent cone of G. And here is when these assumptions are satisfied. So in type A, SUPQ, so most of them. Well, SLNR and this SU star, they cannot be because they're not equal rank. We need equal rank. Then in type B, we have something like half of them. So Q should be bigger than, so the odd parameter should be bigger or maybe less by 1 related to the even parameter. And in type C, SP2 and R is fine, SPPQ are not fine. So they are equal rank, but this representation of Weyl group is not Springer. Then in type D, we have all the equal rank guys. So we have the Hermitian guy, SO star, and also the even. And then in exceptional cases, almost all of them are fine. The only one which is not fine is F4 with maximal compact spin 9. All the others are okay. And then under the above assumptions, let X be a Harish-Chandra module with associated variety of the annihilator equal to this OC bar. So this is this nice class of modules. And then we can express the Dirac index polynomial as an integer linear combination of the multiplicity polynomials. The CK, they are integers independent of X in this family. And moreover, we were able to explicitly compute these constants. So what you get is some binomial coefficients or some powers of 2 and so on, something completely explicit. So for the exceptional groups, we had to use computers. For classical groups, we were able to find some combinatorial proofs. Okay, so now this was the result. And now I'm gonna tell you some ingredients of the proof. So the first issue is this definition of the associated cycle for virtual Harish-Chandra modules. So this was done in another paper by Vaughan in the Park City proceedings from '98. But we use a slightly different version of his construction. It's in terms of the K theory of K equivariant coherent sheaves on the nilpotent cone. We'll come to this in a minute, what exactly it means. So yeah, here it is. So if M is a Harish-Chandra module, then this GRM is a finitely generated module for symmetric algebra of P and K, and it's supported in NP. And now this NP is an affine variety, and then these modules, they can all be localized, and you obtain these K-equivariant coherent sheaves. So there are these localization for affine groups, so it's an equivalence of categories. You have modules over the regular functions, global regular functions. By localization, you get sheaves. And going back by global sections, you get an equivalence of categories. And here we have this extra K action on the global sections and also on the sheaves. So coherent, so quasi-coherent would be anything that's obtained from localization. Coherent means it's obtained by localization from a finitely generated module. So in this way, then we get a map from Grothendieck group of Harish-Chandra modules to the Grothendieck group of K-equivariant coherent sheaves on the nilpotent cone NP. And then what we do, we find a nice Z basis for this Grothendieck group of NP, of sheaves on NP. And our Z basis, we'll see that it corresponds to certain integer combinations of the discrete series representations. And then we can compute somehow both sides and see that so for the basis elements, we simply see by computations that this, so remember that we want to prove an equality like this. So we check it for these basis elements, which are basically obtained from discrete series representations. And the Dirac index is very easy for discrete series representations. And then we have it for all modules by linearity. So how do we obtain this basis? It's obtained from homogeneous bundles on the K orbits in NP. And moreover, it is good that it can be used to express the associated cycle. So let's take an orbit O. It's an orbit of some element E. So you can identify with the quotient K mod Ke. So Ke is the stabilizer of E in K. And then let tau be some irreducible algebraic representation of Ke. So we'll denote the set of such representations by Ke hat. And then we look at this homogeneous vector bundle, K cross tau over Ke. So it's a homogeneous vector bundle over K mod Ke, that is over O. And then we can look at the sheaf of sections. And then we show that it extends, although not uniquely, to a K-equivariant coherent sheaf on the closure O bar. So on the orbit itself, orbit is homogeneous. It's very simple. You just need somehow these homogeneous bundles. And then the issue is to extend it to the closure. Once you extend it to the closure, then you extend it by 0 to all of NP. So that step is easy. So these extensions will be denoted EO tilde of tau. And then the theorem is that these extensions, EO tilde of tau with O running over all K orbits in NP, there are only finitely many, and tau running over the irreducible algebraic representations of the stabilizer, then these classes of these sheaves form a Z basis of the Grothendieck group. And moreover, if you have any virtual Harish-Chandra module X, then write GRX as a combination of these basis elements. And then you can write, from that decomposition, you can read off the associated cycle. It's going to be something like the leading term of this expansion here. So it's the sum over maximal O, meaning maximal dimension, or maximal with respect to closures. And then you have the combination of O bar with the coefficients equal to the sum over tau and O tau dimension of tau. And then one of the points here is that these leading coefficients NO tau corresponding to the maximal O are independent of our choices of extensions. Okay, and then the second ingredient of the proof is a formula for these extensions in terms of virtual Harish-Chandra models of discrete series representations, as I already mentioned. So here somehow, the point is that we are going to construct one particular nice extension for each of these homogeneous bundles, and then for that one we can compute. So how do we get these extensions? It's accomplished using a resolution of singularities of O bar. And then once we have this connection with discrete series representations, then we prove the conjecture by using a simple formula for the Dirac index of discrete series representations. So it's just the lowest K-type with some row shift. It's just a single K-type, which is obtained from the lowest K-type of your representation by a row shift. So we construct our extensions as push forwards of vector bundles under a resolution of singularities. So how do we obtain this resolution of singularity? It's actually due to Constant and Rayleigh. We'll see on the next slide. So let O be one of our K orbits in NP. Let X be a base point. And then this X is nilpotent. So we can construct a standard triple. So SL2 triple X, H, Y. This H can be taken to be in the Cartan subalgebra H. And then the eigenvalues of add H are integers. And so they define a grading of G. So Gm would be the eigenvalue, the eigenspace for H corresponding to the eigenvalue M, where M is an integer. And then we set Pm to be the intersection of Gm with P. And then attached to this grading is a theta stable parabolic subalgebra. Q is L plus U. L is simply G0, so the centralizer of H. And U is the sum of negative eigenspaces. And so we can also consider the corresponding parabolic subgroup in G and its Levy decomposition. So capital letters, Q is L times U. And then here are two facts due to Constant and Rayleigh. So first, the stabilizer Kx has a Levy decomposition with reductive part. You can write this reductive part either as intersection of Lx, the stabilizer of X in L, intersection of that with K, or you can look at K intersected with L and then take the stabilizer of X in that. So these two are the same. And moreover, this stabilizer Kx is contained in K intersected with Q bar. That's one piece of information. And the other is this resolution of singularities. So we said P bracket 2 is the sum of all these eigenspaces Pm with M at least 2. And then this P bracket 2 is stable under the action of K intersected with Q bar. And then you can look at this homogeneous bundle K cross P of P bracket 2 over K intersected with Q bar. And you can map it into O bar by the action map, and you get a resolution of singularities. And then, so we have the resolution of singularities, it's this map mu, and now we use this mu to push forward sheaves or other elements of the Grothendieck group. Sheaves here will be pushed down. And here we can look at some homogeneous bundles. We have mu star and then the higher Dirac, derived images of this morphism mu. And then to get a homomorphism of the Grothendieck groups, you take the alternating sum of these derived functors, derived direct images. And then if you take any representation sigma of K intersected with Q bar, then there is a K equivariant vector bundle like this on this resolution of singularity. And this is the one we push So let S sigma denote the sheaf of algebraic sections of this bundle. And then using the result of a char and some additional computations, we show, first of all, that this what you get by pushing down this bundle is an extension of our original vector bundle on the orbit. And moreover, we can express this extension in terms of discrete series. So there is some finite sum. A goes over positive non-compact roots in L, C goes over roots of this P1, and then we have some sign. And this is the discrete series representation with this is the highest weight of sigma, and then there is some complicated row shift. So you get a bunch of discrete series representations. And one shows that, so you see here, it's only the restriction of this sigma to K, to Kx, but we show that any representation of the stabilizer is a restriction of such a sigma. Okay, and then let's see, I don't have so much time left. I wanted to tell you a little more about these K groups, what goes into the proofs. How do you prove that this is a basis? So it's a little bit more general. So we take just some variety X with an algebraic group H acting with finitely many orbits. And then KH of X will be the Grothendieck group of the H equivariant coherent sheaves. And then there are two basic facts. So if there is only one orbit, then the Grothendieck group of the sheaves is simply the representations of the stabilizer. So I'm sure everybody knows that the homogeneous bundles are the same as the representations of the stabilizer. But in fact, on the level of the Grothendieck group, these bundles are enough to give you all the sheaves. And the second basic fact is if you have a closed H stable subset Z of X, and let U be the complement, so it's open, and let I and J be the two embeddings, then there is an exact sequence. So here are the Grothendieck groups of Z, X, and U. And this I star is the extension by 0, J upper star is the restriction from X to U. And then so it's kind of right exact, and there is something, this first K group appearing here, K1 H of U. So this was defined by Quillen and the equivariant version by Thomasson. And I guess, since I have just a few more minutes, I should maybe start skipping stuff. So you see, our fact is that we claim that we can extend. So you see, we do this extension by some sort of induction. So we start, this U could be the open orbit and Z could be the boundary, so the union of all other orbits. And then we extend, we take one of our bundles on the open orbit, and by surjectivity of this J star, we can get it as a restriction of something, so we can extend. And then it is not unique, but to see that we have a basis, we would like, what is necessary to see that we obtain a basis is the injectivity of this I star. But you don't have a short exact sequence, you don't have 0 here. So how do you see that this is injective? So the point is that we can, in our situation, we can compute these two things and see that although they are both non-zero, there is no non-zero map between them. And this is somehow, so this, by some inductive assumption, this is a free abelian group. And this turns out to be a divisible group. It's some of some copies of C star. It's because this is just one orbit in our applications. So then these are just representations of the stabilizer. And that's, okay, one of Quillen's so-called Devisage theorem tells you that you can pass to semi-simplification. So this H is not reductive, but you can pass to semi-simplification of the category, and then you only have to count multiplicities. So it becomes the K1 group of the category of vector spaces on these multiplicity spaces. And that's one of the examples in A book of Weibull tells you that you get C star for every representation. But then this is 0, this becomes injective, and this is how we prove. This is how we prove that we actually get a basis from these extensions. And I think this is just about time to stop. Thank you very much. Or I should maybe just go to the last slide, which is, yeah, thank you and happy birthday to Gordon.